The next speaker is Professor Shahar Mozes from Jerusalem. I'm happy to have him around, even online, under these difficult circumstances. So he will tell us about locally testable code. Thank you.
So thank you, Koshi, and thanks everybody, Mahan, Nanish, for the invitations and all the other organizers. First thing, I really want to apologize and say I'm sorry for not being able to come. Some of things are, yeah, I don't want to, I mean, they're rather bad, terrible, and horrible, whatever you want to call them, and sad, especially. Anyway, so another thing, so I cannot come, but on the other hand, I'm going to speak about some application of group theory, and it's really into computer science. So since I'm not there, if people are not interested, they can just walk away. I won't see who is going away, so maybe that's an advantage. So it's a joint work with Irit Dinur, Shai Evra, Livne and Alex Lubotzky, and I'm going to write. I prepared pre-written thing, but I somehow usually cannot follow slides talks because they are too fast, so I'm going to write, and hopefully it'll be okay. So the first thing is what we are speaking about. So we are applying groups to error correcting code. So as I said, it's really application to computer science, but there are some groups used, and there's some geometric combinatorial object related to groups, and left-right Kelly complex, we call it, which I think is interesting in its own right, and hopefully maybe you'll find it interesting. So definition. So we are speaking about an error correcting code. So, okay. So an error correcting code. So this is just a subset of F2 to the N. Okay, it's a subset. Okay, so you just think of it as as the zeros, the elements of F2 as bits or zeros and ones, and so these are alphabet. We're just going to use 0 and 1, and you're looking at words of length n, and that's any such subset is called a code. We're actually going to look at special cases where this subset is in our setting. It's always going to be linear codes, which are just linear subspace. Okay, so these are the objects. And there are two parameters that you want from a code. You want it to have large distance, so there are two parameters. One is the distance. So you want code words to be far away from one another. You're sending messages of zeros and ones, and you want the two different messages you send, you want them to be different in many places. So this is the minimal distance between code words. And since we are going to speak about linear code, it's just the minimum number of ones in a non-zero code word. And we're actually going to usually look at the distance is, if you take two words, if you take W and V and C, then the distance between W and V is the Hamming distance, if you want. It's just the number of I of j's between 1 and n, so that Wj is not equal to Vj. We are going to look at the normalized distance. So we are going to look at the distance divided by n. Okay, and the other thing is the rate. So you want to have, so the rate is just measure how many code words. So the rate is, and it's convenient to look at log of the number of code words. So if you want the linear case is just the dimension of the subspace, divide by n. And the idea is that you want to be able to send lots of messages. So you want the rate to be high, but you want it to be far, because so if you think of it, you have this space and these points are the code words, and around each, if they're distance c, then if you take a ball of radius, of radius t over 2, or smaller than T/2 around each code word, then you can correct the codes. Okay, so, and as I said, we are going to look at normalized code. And what you want, so you want, that's classically what people do in networking code, you want high rate and large distance. Okay, so that's kind of classical thing people do in networking code. We are going to look at a special type of codes, which people will, it was open for many years whether they exist, and so this we need the following definition. So these are locally testable codes. So what are these? So suppose we have a code. So we agreed before and on some linear subspace, and I send you a word, you have to check whether it's in the subset. So basically, if it's a linear subspace, it's given by some linear equations, and you can just check all these linear equations, but that may require you look at all this message that I sent, and may be very long. And you could hope that, or you can see settings that you want just to look at very few places in the message and decide whether this is was really belong to the code, or just there is lots of noise and there is no reason to read it at all, because maybe there's so much noise in the surrounding. And so this definition, so let me write definition. And so we have some Q, which is going to be some fixed number, not too large. And you have some kappa bigger than 0. And you say kappa locally testable code with Q queries. Oops, sorry. Is a code, is a code, so that there is a tester, exists tester, so which when given any word, any message, given any word W in F2 to the N, chooses Q bits, or Q, so I'll say Q places, Q bits at random in W, and decide according to that. So the tester look at the code word, choose Q places at random according to some distribution. I'm not saying it's choosing every bit Q times uniformly, just choose some Q tuple of places, and then decide whether to accept or reject. And the main thing is that for every word, for every W and C, if you give the tester a word which really belongs to the code, then the probability of acceptance that you'll say it's okay, or there is a chance of it accept it, is 1. On the other hand, if W does not belong to C, then the probability of rejection is at least kappa times the distance between W and C. Okay, so suppose I give you a code and you're allowed to look only at 7 bits out of the code. You can choose whichever 7 bits that you want. Then you want that if the word is legal, there are no mistakes, then you say, yes, it belongs to the code, or I believe it belongs to the code. But if it does not, then you'll detect it. But of course, if the code word is if the word you receive is very close to the code, maybe the 7 bits that you saw, nothing happened in them. So you can't hope to be able to detect it if the distance is very small. But you wanted if you look at the distance, and this distance is the normalized distance. So this is the Hamming distance we divided before by N. This is the distance between W and C divided by the length of the code. So if there is a, in 1% of the places, it's the there is a mistake, then you'll find that the mistakes with probability, which is kappa divide by 100. Okay, so that's the definition for locally testable code. So such a code is called LTC, locally testable code. Okay, so by the way, I hope that people hear me because there is no feedback, and I hope that it's still working. Okay, so there are people who
I hear you well.
Okay, good. So there's kind of strange to speak just to, since the corona, I haven't taught in Zoom. So anyway, so people were interested in about whether such code exists for various reasons, mostly because so motivation started from what's called PCP, so probabilistically checkable proofs. And this is something that, one hand computer scientists developed, saying that you can check whether a proof is correct by looking at very few papers, but actually we all do it when we write. You get a paper to referee. I think that's, you read random places in it and you decide whether it's correct or wrong. Or that's in practice what's happened, I think. Anyway, this goes back to the 90s. Okay, so this has been around, and this question about whether locally testable codes exist or not is deeply related to PCPs. And of course, we are looking at, we want families, right? So of course, we want family of locally testable codes where the Q and kappa are going to be fixed. And the length of the code goes to infinity. Okay, it's much the same way that people speak, and it's going to appear about expander graphs, right? Or Manutian graph, then of course, we'll take an expander graph, then every finite graph is an expander with some parameter if it's connected, but you want family which grows. Okay, and there was a question whether there are good locally testable codes. What would you mean by good? And so you want so I said that we want error codes. You want to have them high distance and lots of words, and you want them to be able to, that's error code, and you want locally testable. You want to look just at a fixed number of Q. You don't want the Q to the number of places you look to grow as the length of the code grows. So this is what people call you want. So good. So meaning that you have a constant rate. So this is just mean that if you speak about the number of the number of code words, the log of the number, if you want the dimension of the subspace divided by n, you want to be fixed. So you want to have a kind of fraction, the log of the number of log of c divided by n. So this is log of c divided by n is bigger than some fixed r0. You want a constant distance. So this is normalized. So so this is normalized. So again, you can, if you want, you can correct up to 10% of mistakes, and you want to have a fixed locality. So this is Q. So maybe just write Q fixed. Okay, so this was a question. So this was an open question. Are there such codes? And this is open since I think the 19th or beginning of 2000s, and people actually changed their mind. It wasn't clear. There are some conjectures that people, the experts have, strong belief of them, or kind of everybody believe they know what the answer is. This was somehow the same people. There wrote a different time, believe different things. There were periods where people thought such things don't exist, and so they exist, and vice versa. So it went back and forth somehow. So what the main result that I'm going to speak about is actually just a construction showing that this exists. So the main result is the following. So, okay, so this is as I say, joint, if you read the Dinur, Shai Evra, Livne, Alex Lubotzky, and myself, is that for every R, okay, so between 0 and 1, there exists some delta bigger than 0, and kappa bigger than 0, and some q and n, and polynomial time algorithm. It's actually, okay, we can actually make it even explicit. Anyway, construction, an infinite family of codes, CN, which are LTC, which are kappa locally testable with Q queries and rate at least R and distance at least delta. Okay, so that's the result. And these are actually, okay, so these were the first construction, and actually independently, so same time, roughly same time, independently, there's a construction, very similar construction by Pantelev and Kalachev. I'm probably mispronouncing their names. They also gave another construction. They actually use it in this division to construct something called quantum error codes. And anyway, so the two works together were done the same time independently. So what's the construction? So I want to, and in some sense, the reason I'm speaking here is more the construction, even though, you'll see construction, it's very elementary. We spent, I think, more than 2 years trying to construct, going via a very long route. It was supposed to use everything we know. At the end, it's completely elementary. We still believe that the route we were going to could have, I mean, there is some another suggestions object that we still believe maybe give an example, but we don't know how to prove it. But anyway, let's go to the thing which works, which you see is very elementary, but it uses some nice using combinatorial object related to groups. So the construction. So the key ingredients are expander graph or expander, but actually, okay, higher expander, Haley graphs. There's already. And actually, we're going to use higher dimension complexes. So what is an expander? So for definition, so if you have a deregular graph with a lambda expander or lambda one-sided expander, if you look at its adjacency matrices, so it has eigenvalues. Okay, if it's eigenvalues, if the eigenvalues, it's adjacency matrix. So this is just, it's an undirected graph. So it's symmetric matrix, has real eigenvalues. D1, or D, so which is lambda 1. And then the decrease and the minimal one is it's bigger than or equal than minus D. And you want that lambda I is smaller than lambda times D for every I bigger than 1. Okay, so you want all the eigenvalues except the first one to be strictly smaller than lambda times the degree d. And this relates, and if you have such situation, if you look at the random walk on the graph, then it's propagated, it gets mixed. The mixing time is very fast. It has exponential mixing time. These are extremely useful objects in many things, and they're also used for constructing other kind of code. And I want to mention the construction due to Sipser and Spielmann. So they used expanders to construct okay, I'll just I use the name, but to construct nice linear code, so it's what's called low density. So construct low density parity check code. So this is just linear codes with parity check codes. So these are just linear code which are given by a collection of linear equation, which each linear equation has small weight. It's any linear equation and f2 to the n is just, or any function, it just takes some number of bits and take their sum, right? So you want it to be small, okay, with fixed distance and rate. So let me describe that construction, because what we are doing is in many ways just a generalization of this. So what they said, you start with a graph. So you have some d-regular graph. So here, so B5. Okay, so you start to take a graph, d-regular graph, which is d-regular. And okay, you fix some base code. C0 in F2 to the D, just some code on words of length D, where D is the degree of the graph. So we're going to have a family of graphs, or they are going to have a family of graphs which grow and have more and more vertices, but they're all D-regular. And then at each vertex, you see the edges. So you can think of order the edges. And so if we are going to write, zeros and ones at each vertex on the edges. So the codes are W's, which are, so we have a graph, maybe I call the graph, there is V and E, there are the vertices and the edges. So the codes are just maps from the edges to F2, such that at each vertex, so if you look at W and restrict it to the edges at the vertex V, these belong to C0. Okay, so you look at the graph, you write zeros and one on the edges. When you look at each vertex, you look just locally at the edges near this vertex, you see some D tuple of zeros and one, and you check whether this belongs to the code. Okay, and what they showed, what Spielmann showed, that if your graph, if the collection of graph, so I'll just write one graph, but they are, okay, CN. There are lambda expanders. Okay, and their codes and the code C0 fixes delta, which is bigger than lambda errors, you get good codes. You get good error coding codes. Okay, so the basis for this, and again, is a lemma of what's called a lone or theorem, but it's called the lone chunk lemma. which says the following. So we have a graph G, which is vertices and edges. So it's D-regular. And lambda expander, one-sided is enough, but that's it. And suppose you have a subset T of the vertices V. And a subset, so that if you look at GT, this is the induced graph. So not graph. So this is just a collection of vertices, and look at all the edges which in the graph which connects vertices from T. So this is the induced graph. So suppose this graph that you get has the average degree at least delta time D. So some delta is some fixed proportion. This is going to be related to the distance of the error correcting code. If each vertex of T, it has delta time D neighbors in the original graph, then the size of the graph T is at least delta minus lambda times the size of V. And also, of course, you have also lots of edges because that's just because the average degree is large, right? So it's delta minus lambda times delta times Z. Okay, so this is it's extremely useful lemma. It's really, the proof is Cauchy-Schwarz inequality. I mean, once you know it's you know the lemma and you know it's Cauchy-Schwarz, then you can prove it. But what it says that if you have a subset, so this means that if you have a subset T, so this means that if you have a subset T in the V, if you have a lambda expander graph, you have a subset of the vertices, so that if you start at a random walk, okay, so that if you start a random walk starting in T, has high probability, has large probability of staying there, of staying in T, then T is large. This is the way the lemma is the way you say that the expander graph are highly connected graphs. So if you have a random walk and you have said that you have large probability of staying, then this set has to be large. Large means it's linear in the set of vertices in the size of the graph. Okay, and so this is the construction of Simpson and Freeman, and we want to generalize this and but this construction does not give you locally testable code. Also, one thing I should have said at the beginning, all this area of error correcting codes, often when you choose an object at random, it is nice. If you choose a collection of, if you take a linear subspace, even given by low density Bauer-Checks linear subspace, it's going to random one will be a good error correcting code in the sense of we're going to be large. This is just, okay, this depends how many equations you choose, but also it's going to have a large distance. But random one do not give you signature locally testable. Okay, that's an important point. So the random construction do not yield this object that we are looking for, and that also has to do with the thing I said, there is a polynomial time algorithm, right? If you knew that they just exist, then okay, then you can just, in principle, for each n, go over all possible subsets of all the f2 to the n and check them and try to get the code. So this is not the way it works. It's first thing, these things are very rare. Random one, if you choose one at random, the probability you find that it will be a locally testable is negligible. And the construction really works by really construct them in an efficient way. Okay, so the Simpson-Spielman construction use expander graph, and the idea that if you have errors they propagate somewhere along the graph. So we wanted to do something similar, which will ensure that there are errors, and they propagate in such a way that local testability will work. And the idea was to go to higher dimensions. So we want to construct, so we want a code on a higher dimensional complex, on a square complex. Instead of a graph, we're going to work with a square complex. And the one we are going to do is the following object, which is what we'll call the left-right Cayley complex. So this is the object that I promised that's related to groups, which is nice. We think it's nice. And so you have a group G, so G a group, and you have two sets of generators. So A and B in G, two sets of generators. So G is generated by A, and it's also generated by B, and they are symmetric. So A and B, we are going to assume A and B are symmetric, meaning that A equal A inverse and B equal B inverse. So each one of these set of generators contains an element and its inverse. Okay, and then you can associate. Okay, we all know how to associate with a group and a set of generators. You have a Cayley graph. Actually, you have a left Cayley graph. You have a right Cayley graph. So we want to have a square complex. So we have X, we call Cayley AGB, is a square complex. So square complex, you have vertices. So these are just the element of G, the same way that when you build the Cayley graph, the zero skeleton is just the elements of the group. Then you'll have edges. So X1, this is going to be, okay, so it's natural to write it in. Actually, these are just the union of the left Cayley graph and the right Cayley graph. So you take a disjoint union of two sets. So X1A, it's the collection of all pair G, AG. So these are the edges, if you want, of the left Cayley graph of G with respect to A. So G is in G and A in A. And X1B is going to be a collection of all pairs G, GB, again, G and G, and B and B. So you draw all you take the group G, you take the vertices, the elements of G, and you draw it both the left Cayley graph and the right Cayley graph. Think about the edges of XA as being horizontal and the XB being vertical, and then this gives you X2. You have the square complex. So this is, you have squares, you have a collection of squares. You have G, AG, GB, and AGB. Okay, so that's, you add a square for every G and G, A and A, and B and B. Okay, so this is basically, and that's our Rayleigh graph. Okay, this thing you have to think of them geometrically. So you mod it by all the symmetry. This is just think of the geometric realization, and it's going to be convenient to assume all the time some condition that we want that the two sets A and B are really different. So I'll come back to it again, hopefully, is that no element of A is conjugate to an element of B. Okay, so this is the square complex, this is the left-right Cayley graph. And by the way, if we know how to construct something similar, not what I mean, similar with three of higher dimension, not two-dimensional, three-dimensional, be useful. We'll save lots of work in the sequel. So what is the code? So the code is the following object. You choose a finite group. And with two sets of generators, A and B in G, and generators, symmetric sets, and you have X is this left-right calligraph, and you choose linear codes. So the same way in Spielman, there was one base code. So we're going to choose base codes. Well, all of our codes are linear. CA, which is a subset of F2 to the A, CB, which is a subset of F2 to the B, and we are going to define the code C. So depending on all these parameters, C depend on G, A, B, CA, CB, is the collection of all maps. Now we are going to write zeros and one on the square. So you look on the two skeleton of the complex and collection all squares. On each square you write either 0 and 1. So these are just mapped like this. So that for every edge, E and X1A, if you look at the F and restricted to the edges, to the squares touching E, these belong to CB. And if you take an edge E in X1B, then F restricted to the square touching this edge is, sorry, this is CB, and this belongs to CA, sorry. So what is the picture? So the picture is the following. So you have here is a vertex V. There are squares glued around it, and okay, so if you take an edge E, and so this is let's say this is G, and this was GB. So then you have here a 1G, a 2G. For every AI in A, you have a square. Okay, you have a square for each generator is in A. So if you wrote here some zeros and one, you get a word. You can, if you look at a map on each square written 0 and 1, then if you look at an edge and you look at what's written just at the size of A squares which touch it, which have it as on the left side, then you get some words in 0 and 1s, and you want that this word belongs to the code CB, and vice versa when you look at the, if you change color and you look at all the squares which glue to horizontal edge. Okay, so this is a local condition. So this is the type of a condition that we want to be satisfied. And another way of describing this is to say that the code C is all the maps F from X to F2, so that if you look F restricted to some vertex, so let's say to V, so V is in G, X0 belongs to what we call CA tensor product with CB. So it's convenient to think of it. You can look at the squares at the vertex. You have the size of A times the size of B matrix, square written there. So you can write them all the zeros and ones at each vertex as a matrix, and you want that. So you have a matrix of zeros and ones, so that if you look at each row, this belongs to CB, and each column belongs to CA. Okay, so this is the definition of the code. The point is that is the following statement. So proposition, if you want, if G, A and B such that the calligraph of G with respect to A and the calligraph of G with respect to B are both lambda expander. So you want a group G with two sets of generators. So on the same group, you get two calligraphs, and you want both of these calligraphs to be lambda expanded to have very good, and actually we are going to need lambda to be small. And actually, we are going to use the size of A and the size of B. So assume they have the same size, just to simplify our life. And another thing that we are going to need is that the conjugacy class of elements of A, intersection B is empty. Okay, so no element of A is conjugate to an element of B. This I just translated this square complement defined has no kind of edges which are identified even though they shouldn't be identified. You don't want to have the element, otherwise you'll have what we call horizontal edges and vertical edges that could coincide. If you assume this prevent this, and you need the codes. So you need, if you have codes CA and CB, and actually since we are going to have A and B on the same side, you can choose the same code, but this is not really important. If rates row A and row B, and distances delta A and delta B, and with some conditions satisfying more conditions, which I'll tell later. And then you can show that then the code C will be locally testable code. Okay, so there is a, okay, I'm going to, since time, I'm going to jump something, but we want to say the following. So so the condition is that you want the code to be such that if you there's something called a kappa agreement, that there are kappa agreement codes. Means the following, that if you take any word in CA, tensor F2B. So this means just you take a matrix, all of its rows, sorry, all of its columns are in CA, and the rows you don't have any condition. So you have, let's call this WA. And WB is a matrix which is, you don't have any condition on the other direction. So yeah, FT with A, CB. Then there exists W in the code such that the if you look at the probability that WA is not okay. So you want, okay, maybe I'll write the formula and then explain what it is. Probability. Okay, so you're given two matrices. One of them, all its rows belong to the codes, to the given code. All the columns belong to the code. And you want something which really satisfies this, some other matrix whose both rows and columns belong to the code. So you want to say that if you look at the two matrices that you were given, if they differ at very few places, so that's this probability, that's this second probability here, then then both the rows and the columns are very close. Okay, that's the idea. So just some technical, let's ignore it. And the claim is, so the theorem that if we start, oh, let me write it here. So theorem, if X is this left-right Kelly graph, and which are, and this both sorted KGA and KGB lambda expanders, and there's no conjugation codes, and okay, and the codes CA, CB, kappa agreement codes. Okay, then, okay, I want, since given the time and the certain inequalities between the rates, distance, and lambda, you get good locally testable code. So you get a locally testable code with fixed number of query and bounded the distance and the rate are bounded from below. Now, I want to say something about the proof of this, because it's some kind of nice idea, which I think is worth. So the proof uses it's an amusing proof in some sense. So you use an algorithm. You start with what's the idea? You start with I'm trying to think whether I'm going to let me try something, and then maybe it's okay. No, I won't. So what's the? Just a second. Do you still? No. This was a mistake. Okay, so the idea is the following: that you start with a code word. So we define a funnel algorithm. Okay, you given a word, so given a word f from x2 to f2. So this is just so we have a square completely constructed. You're given a word, you want to show that it's locally testable, and basically the idea is to look at the word, and you at each vertex to do the following. So at each you construct an algorithm. So run an algorithm on the code, which stops after certain number of states, after it stops and says and gives either a word in C, a word W in C close to F, or say it's far. Okay. The point is the following, that the number of the number of steps of the algorithm is bounded by the number of vertices where vertex V, where F restricted to V does not belong to CA tensor CB. Okay. I should have said I described the code. I didn't tell you explicitly how you test whether a word is in the code. Okay, so the code was just maps. When we construct a square complex, we wrote zeros and ones on the squares and an element in the code. If each vertex locally you belong to the CA tensor CB. Now the tester, what it does, it chooses a vertex at random and look locally at this vertex whether the squares, whether what you see written in the squares just testing this vector belong to this tensor code CA tensor CB. Okay, so that's the testing. So what you want to know, so this is a local test because you look just at the, sometimes it depends only the size of the generators, and this number of generators is going to be fixed as even though the group G grows. Okay, so now you're going to have an algorithm which stops, and it stops either give you a word and say close or it's far, and the point is the following, that the probability that the algorithm reject if the algorithm finds a nearby word, okay, let me say the following. Let me just say the following. So the observation is the fact that the distance between your given words F and C is bounded by some constant times the number of steps of the algorithm, which is bounded above by constant time the probability that your tester reject. That's if the algorithm stops. If algorithm returns, stops, and it always stops, but if it returns W near F. So this was one option of the algorithm. The second option of the algorithm was that it will just say it's far, and you want to say that in this case, you know that the probability of rejection is large. So the probability, so you also prove independently that if it's the algorithm said far, it implies that probability of rejection is bigger than some epsilon bigger than 0. So, okay, so there's this algorithm which I won't have time to describe, but basically what it does, okay, I'll just say in word, I won't try. So the algorithm take the word that you're given F, it looks at each square, at each vertex, it looks whether it belongs to the belongs to the tensor code or not. And then it chooses each vertex, it chooses a word in the tensor code, in CA tensor CB, which is as close as possible what it sees locally there. So you have this collection of places where what it shows is not what was written there. And then an algorithm tried to improve. It does runs greedy algorithm and tried to fix locally. And at the number of places where there was disagreement that what the algorithm thought should be and what there was is finite. Each time it decreases its number, so eventually it stopped decreasing. And then either it found a word in the code, or it says that it's far. And so this algorithm one has to prove, and this proof uses the ideas of similar to Sipser-Spearman, using this idea that if you have if you work on some graph or here in a complex which has good expansion properties, then if you have certain number of mistakes locally, they should propagate very similar to the long-chain lemma. This thing that there is some technical thing to do there, but that's why you need special code, this kappa agreement of stability, which you did not say what it was. Well, I said what it was. I didn't say how you construct a code like this. Okay, I want to say something about there was this, since it's small part, which is more group theoretic, is how do you ensure? So remember, we want okay, so we want two things for the ingredient. We want nice codes CA, CB. So this means that they have good, they have some good weight, but they are fixed in this, and they are fixed code, so that's not a problem. But you want them to have also that this kappa agreement. That was this nice. And these things exist. These were constructed by work of Irit Dinur, Madhu Sudan, and Avi Vigdorzon some years ago for different reasons. So they showed that such code exists. The other thing we need is a group G with two sets of generators, so that both GA and GB and both calligraphs are lambda expanders. So there are by now lots of constructions, but you want them to have that no element of A is conjugate to an element of B. Okay, I think I have 3 minutes if I correct. So this you want to be empty. So let me tell you how you do this. So the construction of the so there are, as I said, there are various constructions of calligraphy. The one which we try to use is a construction due to Lubotzky. Samuels, and Vishnu. And that's the following, we have the following situation. So what they did is to construct so you work actually in a, with Quaternion group of F2 over FQ to P. And so they construct a lattice, an arithmetic lattice in GL2 FQ T, where Q is some odd prime power. And you define two subgroups, gamma 1 and gamma 2, inside lambda. So these are finite index subgroups. So they're also going to be lattices. So that you want the following situation, that both gamma I, so if you have this group GL2 FQT, this group acts on if you want PGL2 FQT. So these groups has an associated Boas-Titz building, which is just a Q plus 1 regular tree. So you want both gamma I to act freely transitively on the vertices of the Q plus 1 regular tree associated with PGL2 FQ over this field. And in such a way, okay, that if you take now, okay, so that's I want to say. So that you have sets and there exists set of generators, so A in gamma 1 and B in gamma 2, so that gamma 1 is generated by A, gamma 2 is generated by B, and the elements of A, all elements of A have order 2, okay, and all elements of B of infinite order. Okay, that's really the main observation here. Okay, in such a way that there exist congruent subgroups lambda, so that if you look at the quotients, okay, so if you look at at lambda model these congruent subgroups, you get PGL2. So I'm mistake, just a second. So yeah, PGL2, yeah, Q to the E. With the field, you have finite groups of which are isomorphic to PGL2 or actually PSL2 of the Q to the E, of fields of Q to the E elements. Now what will happen? So and this all so that what you'll get is that the images, so if you have this maps phi, so phi, you have map phi from from lambda onto this PSL2 Q to the E is going to grow. E is going to grow to infinity. Okay, so you have a sequence of such maps, and such that the Cayley graph of PSL2, and I'll stop here, sorry. With respect to the image of A or of B, they are both going to be Ramanujan graphs. So they're going to be extremely good lambda expansion. And what will happen that here the generators are of order 2 always. These are, so this PSL2, so we look at the group G or family of groups is PSL2 QE, the 2x2 matrices or a field of Q to the E elements, determinant 1. And we make an structure for a Ramanujan graph, one with generators of order 2 and one with generators of order bigger than 2. So then they cannot be conjugated. That's the other ingredient. Okay, sorry for being over time. So I have to stop.
Thank you. Are there any questions or comments?
Hello. So I have a question that towards the beginning of your talk, you had this deregular graph from where you had constructed a code.
Mm-hmm.
So in that, you said that in the neighborhood, if the sequence is a code word, but what is the order with which you decide?
Some arbitrary order. Doesn't matter. Each vertex should choose an order. There's no just any way you want. Later in the Cayley, in the square complex that we constructed, then the order was given because there was a labeling of the edges coming from the generators. But in the original the construction of Spielmann, you just choose it arbitrarily at each vertex. There is no whatever choice you want.
Okay. I was wondering this because changing the order would, I would guess, dependent on the
Yeah,
base
you'll
spot.
get different codes. You'll get different codes, but they all have the same expansion.
Okay. Thank you so much.
I mean, I don't know if they're essential. They all have good expansion. Maybe, maybe there are some better choices or no, but yeah, but it's not important. Thanks.
Any other, Maham?
Yeah, thanks, Shahar. So why are you using function fields over QP instead of, I mean, could you do the same thing, say, for example, for irreducible lattices in SL2 QP cross SL2 QP?
The problem was here that we noted there this condition that we wanted. This was only for getting A and B, which are not which no element of A is conjugate to an element of B. And so this is, and somehow we did it this way because that's the way we knew, and somehow okay, this was not really to have this condition that the no element of A is conjugate to an element of B is. Personally, I don't think it's really important for that. It somehow simplifies. It's. What it guarantees that you don't have this coincidence that a vertical edge is identified with a horizontal edge, which simplifies your life.
Okay.
So the answer is that one thing this is not a crucial condition. This kappa agreement of the codes, this thing which uses the work of Dinur, Sudan, and Wilson. This is important for us. But this non-conjugate is really to simplify our life, and we use this this type of lattices just because there we knew how to do it, to have this trick of element of it was an amusing thing to think how you construct, you know, the same group, two set of generators, both of them give you good expansion. These people knew how to do, but you want to make sure that no element in one set is conjugate to an element in the other one. Okay, so this is the nice thing. It's a fun thing to realize that if you make them the different orders, right? That one has elements for order 2 and the other orders, that's something which is invariance. But the answer, it's not, there is no canonical, it's not for some canonical reason. It's just the way we knew to do it.
Okay, thank you. Yeah.
Any other questions or comments? Maybe I have one. So maybe I'm missing a point, but why does expansion helps for you to construct a good code?
Okay, yeah, that's the fact that the part that I completely skipped is because I didn't really describe the algorithm. Remember, you see, you take a vertex, and what is the, so you have a vertex, and the thing that you check is whether you look at so you have, you know, I don't know, q plus 1 squares, q like 1 to the power 2 squares glued at it, right? And you begin writing them zeros and ones. And now you look at one vertex. Recall in the Simpson-Spielman thing, if you had one vertex and you have some place where there is a mistake, then you had this vertex there, since the code has certain distance, it has many edges which were wrong, so there was a mistake at many places, and this somehow propagated. So you want also here you have one square where you have this one vertex in which this pattern of zeros and one that you see is not in C8 and tendor CB. It means it's far from the code word. And this implies that so this means, okay, so there's kind of, I have to draw this. So there is, and if you look at this vertex and you see what is the okay, there is the local code word near this vertex, the closest thing. There is one near this one, and suppose it will be kind of vague, but if you look at two adjacent vertex, G and AG, and if suppose they disagree, if there is an error, then locally there is some disagreement between them. But this implies there is another edge which have disagreement, and these edges of disagreement propagate. And these edges of disagreement, these are the things which your local testing detect. Okay, it's without spending another 5-10 minutes about the algorithm. I can't give a good, but it's basically the same thing that the Simpson-Spielman did in the graph. Here this expansion tell you that if you have a certain vertex, or if you have a word which is not in the code, it means that at some vertex locally what you see is not in the code. Okay, but conceivably the problem could be that you can have change only one, that you can have mistakes in very few places. In most places they're okay, but still the code word which is near it has to be different in lots of places. So you'll have, you really are going to be very far, but you won't detect it by this local test. And this propagation ensures that this does not happen.
Okay. Thank you. Any other questions, comments? Okay. In that case, let's thank Shahar again.
No, thank you, and I apologize again for not being able to be there and missing it. I would really love to be there. It's much better than.
Anyway, thank you very much. And it's quite early there. So thank you very much for taking all this trouble. Yeah.
Thank you.